Good morning, good afternoon, good evening. I want to thank everyone for taking the time to join us. My name is David Cantor. I am one of the founders and the head of MLPerf at MLCommons, and it is my pleasure to kick off this presentation and share with you, with my esteemed colleagues, what's been going on in MLPerf Inference in the last 6 or so months. So this is the Inference version 5.1 briefing. Just as a reminder, this entire meeting is under embargo until September 9th at 8 a.m. Pacific time, and we will be recording the first portion of this meeting, which will be made available to folks afterwards. So I'm joined by quite a large team who contributed to MLPerf Inference: Scott, Miro, Frank, Virat, Keith, and Taran, as well as we have many submitters on the line here. So we've got a whole host of folks, and then our esteemed friends in the press and analyst community. If we could go to the next slide, please. All right. So as a reminder for folks, if you're a member of the press or analyst community, there are a number of documents that we provide to you, all under the September 9th embargo in the Google Drive. You should have a copy of the results, the supplementals, the press release, and I think this time around we have 3 blogs about our new benchmarks. And those are sort of more in-depth dives into the who, what, where, why of those benchmarks. So you hopefully have gotten a chance to look at them. If not, you'll be able to access them. And then the recording of the first portion of this meeting, of the scripted portion, not the Q&A, will be made available through the Google Drive. Next slide, please. So this is the agenda for today. I will be handling the MLCommons overview. Miro, one of the co-chairs, will be talking about MLPerf Inference and the benchmark suite more broadly and the results. And then we will be passing it off to Virat, Keith, and Taran, who will each get to talk about one of the new benchmarks that they helped to lead on behalf of the organization. And then we have the customary Q&A at the end with all of the submitters. Next slide, please. MLCommons is a nonprofit industry consortium. Our mission is making ML better for everyone. And we have well over 125 members spread across the globe on 6 out of the 7 continents. We're still looking for someone at McMurdo Station, so if you know them, give me a holler. You can see the logos up on the screen here of our various supporters. And in addition, we have many individual members. And while many of the logos here are from industry, we also have broad participation from academia. That's actually something that we're going to be seeing in this benchmark suite. We have submitters from academia, which is quite exciting. Next slide, please. Within the broad goal of making AI better for everyone, how do we go about doing that? And the answer is we are at the nexus of research and development, sort of the cutting edge here. And we really focus on how we can measure and improve various aspects of AI, particularly around data, which is the fuel for AI, and gives rise to accuracy, as well as the speed and efficiency. And so within MLCommons, we have projects broadly in 4 different areas. We have work around data, for instance, the Croissant standard, which is a standard mechanism of describing a data set and making it legible to AI. We have work in our research community, such as AlgoPerf, which is a competition focused on algorithmic efficiency in AI training. And we also have a newer project looking at AI risk and replicability and sort of taking all of our chops in benchmarking it and applying it to some of the challenges in looking at the outputs of deployed AI systems. But today, front and center, the star of the show and the first project within the MLCommons family is MLPerf, which focuses on how we measure the speed as well as energy efficiency of AI training and inference. And one of the things that I'm really thrilled to announce, if we want to do the next stage of the build, is we have hit 90,000 results within the MLPerf family. So that's a very exciting milestone, and it's great to get to share that with everyone today. Next slide, please. So MLPerf is a set of benchmarks focused on how we measure the speed and efficiency of AI and AI systems. And these are the goals underlying behind the design of this benchmark. We want our performance measurements to be reproducible. That's the basis of the fundament of the scientific method, right? If you want to measure so that we can improve, we need repeatability. We need our measurements not to be jumping all over the place. That is something that gives us trust, that allows us bringing together buyers and sellers, researchers and engineers, the broad community. We want our workloads to be representative. First of all, representative workloads measure important things commercially and let us focus in on the things that are pressing today and in the AI systems that are being deployed and developed today. It also ensures that all the effort we put into this benchmarking, which is not insubstantial, especially on, from our submitters, gives benefits to the whole community. We want AI to get faster and more efficient for everyone. And this is all done, through the MLPerf and MLCommons process, which is, focuses on being transparent and fair and ultimately useful, right? We need to have a level playing field so that everyone can show off their innovations, their architectures on a fair and level playing field for everything from the smallest startup to the largest companies, regardless of whether your innovations are in software, in hardware, or even in data sorting. And this is one of the things that allows us to help highlight innovation, to serve both the commercial and the academic community, and ultimately keep benchmarking not just a fair and level playing field, but one that is open to everyone. Next slide, please. Machine learning is ultimately a multifaceted problem that spans the whole system, from the lowest level of transistors and packaging to how we sort data, to networking and software, as well as system scale, right? How many processors, how many accelerators there are in a system, and how they work together. And this is both great because it gives us many different avenues to improve performance, to improve efficiency, but it also makes the measurement a little bit challenging because we have to account for all of these factors. Next slide, please. The MLPerf suite has grown tremendously over time in both depth and breadth. And on the left side here, you can see the breadth, which is that MLPerf training was the first benchmark. And over time, we expanded into inference and then into verticals. For instance, our MLPerf automotive benchmark, which was released in the last couple of weeks, and into specific form factors, such as mobile and client, which, client also came out earlier this year. So that's an example of how we broadened our ability to measure AI as AI has, become touching almost every aspect of computing, but we've also gone deeper and matured our ability to measure. So this includes things like adding power measurement for not just solo systems, but things in the data center, like those used for at-scale training, additional metrics, releasing apps on various platforms that put the measurement tools in the hands of more people, and staying abreast of the rapidly changing ecosystem and workloads. Next slide, please. So I'm pleased to turn the next section of the presentation over to Miro Hodak, my friend and colleague, who is one of the co-chairs of MLPerf Inference. So without further ado, Miro, please take it away.
Okay, thank you, David. Let's move on to the next slide, please. So I'm presenting this on behalf of the MLPerf Inference working group, where I'm one of the co-chairs. And as David said, this is actually the place where the collaborative engineering taking place. We have, our member companies. We have weekly meetings where we have meetings with our member companies, and we come together for two primary purposes. One of them is to create and develop benchmarks that are following the field, that are tracking what's the latest, what is the state of the art, and developing the benchmark fully that would sort of be a full, that is not I will show you some of them, but basically we bring things that combines what is the model, what is the data set, what should be the things that we are measuring. And once those benchmarks are there, the second part of the activities is actually running submission and publication, which is why we're meeting today, so that any result that you will see as a part that will be published during this round have undergone the peer review, so that the results have been validated through this cross-industry collaboration. Let's move on to the next one. So I've covered what we do within the working group. The important thing is that we also cover both data center and edge system. I will go through that in more detail, but there's some of the overlap between those two divisions, and there are also some differences. So let's move on, please. So the MLPerf Inference benchmark definition at the high level sort of stayed the same since the beginning, since the inception in 2019, so about six years ago. It was really you take an input and run it through the model, you get some sort of result. What is shown over here is basically how things work when sort of image processing has been the state of the art. So if you took a resonant model, you can take image and it would be classified as CAT, for example, right? The overall structure, while models have changed and we have different inputs and outputs now, the scheme is pretty much the same. So nowadays it would be more like we take some sort of query, we run it through LLM, and we sort of generate an output based on that. So this type of structure we continue to use because it's pretty simple and straightforward and continues to work. We have multiple submission divisions. We have a closed division in which there are strict rules for what submitters can do. Submitters can go and they can optimize the implementation to their hardware to fit best their hardware. However, they have to meet the strict rules of mathematical equivalency so that they still solve the same underlying problem. And as a result, all the results that you see in this division are directly comparable to each other. In open division, things are a bit different. This is where we sort of open up the rules a bit. So we allow space for innovation along the dimensions of model and algorithms. And oftentimes these results actually show significant improvement over what you see in closed, but because they solve a problem that now is defined differently, the results you see in open division cannot be compared to closed division, nor they can be compared between other submission in open, because every submission usually is doing something different. But we have these two divisions that double purpose, being both satisfying being both comparison and also allowing algorithmic innovation. Let's move on. So we have different scenario in order to sort of provide a complex evaluation of performance. The one that is shared for every benchmark is an offline type of scenario. This is a scenario in which entire data set that needs to be processed is available in the beginning, and we basically measure how long does it take for a system to process this data set. This is a very sort of kind of like a brute force type of measurement where we really just measure the raw computational throughput of the system. When we are in data center, we usually require another type of measurements, which is a server type of scenario. In this case, the samples arrive with certain frequencies. So this would sort of simulates effectively serving the model, right? So the queries arrive according to certain frequency, and the system has to process them within a certain latency that is defined. Now, latencies vary according to the benchmark. I will go through that, but this is sort of in data center we usually require these two measurements. When we look into edge system, in addition to offline, we also have a single stream. So the way single stream works is that there are that queries arrive singly, and and system process the single query, and once it's done, we sync with that one query, and another one comes in. Multi-stream is very similar, except instead of one, you process several in one go. Let's move on. So looking into sort of possibility, several divisions that we have in the 5.1, I've explained to you closed and open division. We also have we also classify hardware according to its availability. We have 3 classes. One is available, so something you should be able to get right now. Also preview, so something that will be commercially available very soon. Or we have RDI division for research development internal systems, something that that is internal and usually cannot be obtained. Looking into this matrix, when we sort of put availability versus closed and open division, you can see that most of the results has come from available data center submission, which is sort of historically has been true. So this is sort of where most of the interest in MLPerf is, and this is where that actually provides us a wealth of number to compare different systems between each other, with each other, and get some conclusions based on that. We also have some of the submissions in on the edge and in open division. Let's move on. Now, looking into what we have in our inference suite, I mentioned that sort of working group works on defining new benchmarks, and this has really been lately has been very I guess difficult and very, it's trying to follow what's happening in the field has been challenging, but you can see that we've been managing to follow the trend where we see that the models are becoming progressively larger. And we have in last few rounds, we introduced our 2 models, the largest models that we ever had. So in 5.0, we introduced Llama 3.1 405B. Now we introduced Llama DeepSeek R1, which has close to 700 billion parameters. So, and that's definitely that the growth is showing over here. I will overall, if it's do an overview what's new within the benchmark, there are 3 new benchmarks. Where we'll have task force chairs giving you some more details on this. But briefly, it's reasoning with DeepSeek R1. So this is our very first reasoning benchmark. We also will have a speech-to-text with Whisper model. We also have a small LLM based on Llama 3.18 billion. We have a version for it in Edge. And in addition, the speech-to-text is also available for the Edge. Let's continue. So in addition to the new benchmarks, we also keep introducing new interactive scenarios. So I told you how our server works, that under server scenarios, the queries have to be answered within certain latencies. We have this set up for a while. And one of the things that have been sort of asked from the community has been that there is also a demand for significantly lower latencies that we have done when we first time defined the benchmark. So in order to capture this trend as well and provide performance data for that, we are now offering also for some of these benchmarks, offering tighter latency constraints, and we call this type of scenario interactive. And as you can see, we right now have this in 3 benchmarks, and that is Llama 270 billion, Llama 3.1405B, and Llama 3.18 billion. In this case, our submitters, when they submit for data center, can submit 3 options that will be offline, server, and interactive. And goal of our working group is that we actually want to extend the coverage of our interactive close to most of the benchmarks that we have in the suite. And that's one of the things that is in progress. Let's continue. This is just an overview of all of the benchmarks that we have. We don't have time to go over everything, but we have 10 benchmarks for data center and 8 benchmark in the edge. This is the basic definition of the benchmark. As I said, it is always what is the model, what is the data set, and there are other things coming to that as well as a performance and accuracy metrics. All of that is available on our website and can be sort of looked up with more details there. Let's continue. So overall, we have over close to 1,500 results from 27 submitting organizations. I would specifically want to call out our new submitters for MLPerf Inference, which is MyTech, Nebius, Stage AI, University of Florida, and Vulture. We also have several submissions for the power results, which is very important for the industry to understand what the power consumption of AI model is. We have closed results from Lenovo and open from Gate Overflow. Let's move on. And if we look at sort of total submission per benchmark, we can see that this basically gives us what is the most popular for our submitters. You may notice that that it's not some of the most exciting ones, but this is more of a mix because the exciting ones are the ones that submitters definitely want to do, but also the ones that are sort of easier to do or that have a longer history within our suite are the ones that actually receive a lot of submissions. And in this case, we have a Llama 270 billion being for the second round in a row, being the main our most popular benchmark. And because of the wealth of the data, I will actually show you some of the. It's actually a good case to show some of the performance improvements we have seen over the last few rounds for large language models. Let's go to that in the next slide. So we definitely can see that there is continued momentum around generative AI. As I mentioned, for the last few rounds, Llama 270 billion has been our most popular model, and we can see that the number of submitters continue to rise. Let's continue. Looking at the performance, this is actually a good proxy for estimating or getting some good data on how much the performance can improve for the same benchmark. We have introduced Llama 270 billion in 4.0, which is a year and a half ago. And when we look at the median score from that submission compared to now, we can see that it's 2.3x faster. We have also, if you look at the best score, that one actually jumped by 5x, and these are really great numbers. The contributors to that, there's several contributions to that. We cannot maybe go into all of those details, but we definitely now have seen that this benchmark has been submitted on larger system scales, and moving to FP4, numerical precision also brought significant improvement in performance. The bottom plot also shows the performance per accelerator. So take away the system scale, and even in that case, the performance improvement over a year and a half has been significant. Let's continue. As we also in some of the new things in this round are that we have new processors, we have new AMD GPU, we have Intel Arc Pro GPU, we have NVIDIA GB300, NVIDIA RTX Pro 6000, and NVIDIA RTX 4000. Let's move on. Now, the final thing I guess I would say is that when the results are sent, and also when the results are displayed on the website, it's a bunch of numbers, and there are multiple ways how to sort of make stories out of that. I showed you one for our most popular benchmark, but there's definitely many more ways of how things can be sliced and diced and compared. And there are a lot of actually interesting stories hidden here. So I would encourage press to sort of dig into these numbers, and oftentimes it actually makes sense to just focus on a thing that are similar across some dimensions, but different across others. Also, it is interesting to see what is the performance scaling over time. It could be due to new hardware, software, because we can see that this sort of continues. Also, I would like to acknowledge that a lot of work going into the result from each submitters. We have chip makers who optimize benchmark to best fit their hardware. And you can see that the benchmark compared to reference code, they achieve several times the improvement performance that is several times faster. We also have OEMs and CSPs that brings the developed code and optimize it to best fit their hardware. So there's a lot of interesting things to do. And with that, if we move on, I think we come to the part where we get our task force chairs, who have done hard work in developing some of these new benchmarks. They will give us overview of the new benchmarks that we have, and we'll start with Virat, who will walk you through our very first reasoning benchmark that is based on DeepSeek R1. Virat, please take it away.
Thanks, Miro. Can we have the next slide, please? Thank you. So DeepSeek R1 is a 671 billion parameter mixture of experts reasoning model released by DeepSeek AI Labs in January 2025. Of these 671 billion parameters, 37 billion parameters are activated for any given token. Our goals for adding this new benchmark have been is to test platforms on cutting-edge reasoning large language models using realistic and tough tasks. We want to enable longer output sequence lengths, which allow for these step-by-step solutions the reasoning models are capable of. We want to use diverse, high-difficulty datasets, which span across different domains like math, code, science, multilingual, reasoning, etc. And we want to set practical accuracy and speed targets for real deployments in order to best represent commercial use cases. Next slide, please. So the DeepSeek R1 model introduced a few new innovations. Those include additional sparsity in the feed-forward network and a new attention block called multi-head latent attention, among other improvements. These offer challenges to the submitters, like sustaining accuracy and coherence over very long output sequence lengths can be challenging. It can be challenging to handle these complex task types in our ensemble dataset. It is difficult to manage these large mixture of expert reasoning models and the high resource demands they have. And overall challenges will have to find their balance between speed and thorough model thinking in order to achieve the best results under the given constraints. Next slide, please. The data set we are using to test DeepSeek R1 is a mix of samples from AIM, Math 500, GPQA Diamond, MMLU Pro, and Live Code Bench. These cover difficult benchmarks across knowledge reasoning, software engineering tests, multilingual, and reasoning tasks. The mean input and output sequence length of this dataset is 800 and 400 respectively, 4,000. The 4,000 mean output sequence length includes the thinking tokens. The metric we use to evaluate these samples is code execution for the live code bench coding style questions and exact match to the ground truth answer for the other knowledge-based and reasoning benchmarks. The server, let's go, yeah. The serving latency we have chosen is 2 seconds for the time to first token 99 percentile and 80 milliseconds for the time per output token 99 percentile. Next slide, please. I will allow now Keith to introduce the speech-to-text benchmark that we have added.
Thank you, Virat. I'm Keith Acorn, and I'm the task force chair for our new Whisper speech-to-text benchmark. In this round, the MLPerf Inference working group took interest in a new speech-to-text benchmark. This decision was driven by increased demand for high-quality text transcription in enterprise, consumer services, and as input for other AI interfaces. The task force set out to develop a new speech-to-text benchmark with two main goals: maximizing accuracy across a range of domains, and supporting a wide range of deployments from edge workstations to large-scale data center clusters. To compare performance, we measure the throughput of tokens generated by the model, which correlates to how quickly text is being transcribed. Next slide, please. The task force evaluated a set of ASR models for this benchmark, but quickly aligned around Whisper Large V3, which is a transformer-based encoder-decoder model with approximately 1.5 billion parameters. There are several reasons why Whisper was selected. First, we took a look at accuracy across a range of data sets to avoid choosing a model that had been fine-tuned for a specific data set. Whisper models scored highly across a broad range of content, and of these, Whisper Large V3 considerably outperformed the rest. Next, though we did not test this directly, Whisper was trained with an extremely large and diverse collection of data, some of which deliberately added environmental noise to make it more robust in real-world situations. Finally, we gauged community interest by looking at leaderboards for recent downloads, developer sentiment, and academic citations. Whisper was the top of each of these, indicating broad community adoption. Next slide. This is an overview of the new benchmark. In addition to the Whisper model, we're using the Libre speech dataset, which remains a widely used standard for ASR benchmarking. We customized the sample durations to improve efficiency with Whisper's architecture. Applying standard text normalization, the reference accuracy is 97.9%, which is a substantial improvement over the retired RNNT benchmark, which had an accuracy of 92.5%. For this round, we enabled offline mode only. However, we're investigating whether to include server mode for a future round. Finally, we reviewed the final submission data, and we're pleased to find that 14 vendors submitted Whisper benchmark results across a wide range of systems. Of the 37 systems measured, the performance ranged by a factor of 430x, demonstrating a wide range of hardware and software support. Next slide. Thank you. Next, Taryn will introduce the small LLM benchmark.
Thanks, Keith. I'm Tarnanga, and I was the task force chair for the small LLM benchmark. So in enterprise, we know there's a growing demand for low latency LLM inference. And reflecting this, we refreshed our benchmark that is to replace the previous existing GPT-J model and to bring it up to date to the industry standards through various improved metrics, a new model with a much longer context length, as well as tokenize the word count, and adding more relevant test case scenarios. Now, accurate text summarization is useful for several applications like automated reporting and knowledge extraction. And following this benchmark captures multiple metrics such as throughput to output tokens per second, multiple latency constraints, as well as having a high root score for accuracy. This allows for unique hardware and software optimization opportunities, delivering high quality solutions across various systems by our submitters. Next slide, please. Before I get to this, the task force found the following model and dataset suitables for this benchmark. So the model choice was the Llama 3.18p due to its popularity, reasonable size, and low barrier of entry for LLMs, and the longer context length as well as higher word count tokenizer, improving over the previous one of GPT-J. The dataset was carried over from GPT-J, which was the CNN Daily Mail, also due to its popularity for text summarization tasks, as well as having a unique longer input length and shorter output length combination in our benchmark suite. Now, to cover real-world responsiveness, multiple scenarios with different constraints are being tested. There are two of these constraints primarily. The first would be the time to first token, which is the time taken for the model to process all of the prompts provided. And second is the time per output token, which measures the time taken for each subsequent token, which is generated sequentially while we're using the prior processed context. The throughput in these scenarios cover different deployment use cases. The larger constraint, which we call a service scenario, is effectively giving us over 480 words per minute, which allows for efficient enterprise responsiveness for high concurrency and is suitable for general purpose applications. Meanwhile, the smaller constraint, which we describe as interactive, allows for over 1600 words per minute. And this results in having a high tokens per user and giving much more immediate feedback for applications such as chatbot and questionnaire answering. This necessitates differences between user experience and test the submission systems for different performance envelopes. Now giving it back to you, David.
All right. So thank you all very much. just as a heads up, as I said, the embargo is till September 9th in the morning. The results will go out, and we have timed the release of results to coincide with the AI Infra Summit in Silicon Valley. I will be speaking there, and Miro will also be speaking and giving sort of a deep dive on the benchmarks in a session there. It should be actually fairly familiar to the content here. But I hope you all join us, and we would love to see you there.